Hi, everyone. Thank you for hosting us. My name is Janine Turner. And yes, results, well, this is work in progress, so I do have some preliminary results, but this isn't submitted yet anywhere or anything. So I'm going to be talking about Bayesian word sense discrimination. And so first of all, I'm going to talk about, for a moment, what word sense disambiguation is. And that's just given some ambiguous word, such as bank in this case, which could be river bank or financial bank, or even bank as in turning as in an airplane. And given the word's context, either words surrounding the word or dependency information around the word and so on, and a set of possible meanings, figure out, and label training data, which means examples of the ambiguous word along with the labels. Try to figure out which sense the ambiguous word takes. And this is a supervised problem, and so obtaining a lot of labeled training data necessary for this task is an expensive process. And so a lot of people have looked into unsupervised learning in order to avoid the knowledge acquisition bottleneck. So I'm going to compare word sense disambiguation, which I just mentioned, to word sense discrimination, which is an unsupervised learning task. You still get the context around the word, but you don't get the possible meanings. You just know it's an ambiguous word, and there may be some number of possible ambiguous meanings. And you don't get any labeled training data. There's two kinds of word sense discrimination. The first kind, you do get some outside labeled data. You might get dictionary entries or thesaurus categories or other things like that. But it doesn't quite fit the machine learning definition of unsupervised learning. But the second one, where the only data you get is from the context of the word, that's sort of strictly unsupervised. And we'll be talking about that. So ambiguity in words is fun. WordNet lists 30 senses for the word line. That's kind of a lot. Some of them are very distinct and easy to tell the difference between. A formation of people or things one behind another, as in, I stood in line at the movie theater. Text consisting of a row of words written across a page or computer screen. I read the line of text. And something that is long and thin and flexible, such as a clothesline for drying clothes. Sometimes the distinctions are way too fine, such as these are two definitions in WordNet, a formation of people or things one behind another versus a formation of people or things one beside another. And these are distinct senses in WordNet, but pretty hard to tell the difference between, and not all that useful in most cases. So why do we care about word sense disambiguation? The first obvious reason is to do correct semantic interpretation, but there's also a number of applications, such as in machine translation. If the ambiguity doesn't extend across the language, you want to figure out which sense it is before you translate it. Also in question answering and information retrieval, it's good to be able to figure out, again, which ambiguous meaning the word has. And also in language modeling, you can possibly improve performance by knowing which sense is coming in this word. So there is quite a bit of previous work, both in supervised word sense disambiguation and also in discrimination. And I'm not going to talk anything about the disambiguation. But in discrimination, there are some interesting work. First of all, Urowski takes information from Roget's thesaurus categories and uses that to classify ambiguous words. Later, he also takes seed collocations. So in the ambiguous word plant, he says, well, life is one possible sort of related word, and manufacturing is another possible. And so he bootstraps that and grows more information from those words. Eisner and Karakos decide that they want to choose the seeds automatically, so therefore making it a fully unsupervised task. Schütze just uses the context information and uses expectation maximization, which is a common machine learning unsupervised technique. Peterson and Bruce just use clustering methods to cluster the contexts of related words. And Pantel and Lin do something a little bit differently, but it's related. They cluster all the nouns in a corpus and sort of compare them, and they do some synonymous tasks too. So why are we doing something new and different for this? There are some downsides to previous unsupervised discrimination. Expectation maximization prefers the groups to be similarly sized, but word senses, usually there's one that's much more common than another. In the Penn Tree Bank, financial interpretation of bank is going to be much more likely than the River Bank interpretation. And most of the methods previously done, you need to tell them how many groups there are. Or if not that, then give it a cap. Peterson and Parande and Peterson give it 7. They can't have more than 7 senses. And some of the unsupervised methods, again, as I said before, need outside information. So what do? We use a Bayesian generative model for unsupervised learning, which I will discuss in much more detail. And we have 2 models. The finite model is, we do give the number of senses. We tell it how many there are. And then we extend the finite model into an infinite model, where we don't know the number of senses. Good things about this approach are that, again, as I said with the EM, the groups are roughly the same size. This model can handle data with senses of varying sizes, where one is much more common than the other. And as I said, the infinite model doesn't constrain the number of senses. So we use context information in our model, and we have 3 different things we tried. These are just bag of words feature sets where we just count the words in the local context. And first of all, we try all nearby words, just the sentence or sentences before and or surrounding the ambiguous word. But there's a lot of noise here, things that aren't that useful. So we also look at a stripped version of the full parse, which is basically just taking the full parse and turning it into a sort of more function argument notation, loosely inspired by tetragrammatic form. And then finally, we do another even more simplified one where we take out the closed class words in addition to the what we get from the stripped version. Okay, so I'm going to talk about the finite generative model. First, we have a probability over possible senses, W. So this means if we have two possible senses for bank, maybe financial bank is 75% chance and river bank is 25% chance. So that's all the probability distribution means there. And then for each possible sense, we have a probability distribution over the context words. So if we've chosen riverbank, then we have another probability distribution that addresses the words that we see, bank versus river and things like that. For those who care, these probability distributions W and theta sub z are chosen from Dirichlet distributions with hyperparameters alpha and beta. And so the generative model talks about how we generate the data we observe, i.e. the context words surrounding the ambiguous word. So first of all, for each instance of the ambiguous word, we have a whole corpus full of instances of bank. And we go through, and for each instance, we choose a sense from this distribution over senses. Once we have a sense, then we generate probabilistically guess M context words from the sense distribution. Stop me if you have any questions, if I'm losing anybody. The infinite model is very similar to the finite model. The main differences here are, again, for people who are interested, W is now drawn from a Dirichlet process instead of a Dirichlet distribution. And sort of the main difference here to talk about is that you can either choose a previously seen sense. Say we had two senses already, riverbank and financial bank. We can choose a whole new sense. Say this one is too different from the other senses we've seen so far, so I need to have a new sense for it. But everything else stays the same here. So I've defined a generative model, but what does that mean? What do we want in order to do word sense discrimination? We want to find a sense for each ambiguous word such that the probability of all of these senses given x, which is the context words, and our hyperparameters alpha and beta. So just the most likely set of senses, essentially. But we can't compute this directly, so we're going to use a sampling method called Gibbs Sampling, which is well known in the machine learning community. So Gibbs sampling. So if we still have the ambiguous word bank, first we put every instance of the word bank into one group. And then for some number of iterations, for each instance of bank, we take it out of the group and choose a new sense for it, either putting it back where it came from or in a different group, different sense group. And over time, the sense assignment should converge to a sample from the joint distribution, and then we're done. But what I didn't say is how we choose a new sense for each one on the iterations. The probability of picking a new sense assignment is just a combination of two probabilities. One is the probability of the sense, as before, chosen from that distribution over probability over W. And then you have the information is all the other sense assignments and the hyperparameter alpha. I'm going to go into more detail, so if I'm confusing. And also, the other probability here is the probability of each context word, given all of the sense assignments that we have, all of the other context words, and this hyperparameter beta. So in both the finite and infinite models, the probability of a sense is just proportional to the current number of instances of the ambiguous word that have that sense. So if currently there are a lot of instances of financial bank, but not that many instances of riverbank, then it's going to have a higher probability of choosing the sense financial bank for this particular instance of the ambiguous word. The difference in the infinite model is that in addition to having this decision proportionally between existing senses, it can generate a whole new sense. And this is just a probability that's dependent on this hyperparameter alpha. That's where alpha comes in. And so remember, the probability that D is a combination of the probability of the sense and the probability of the context words. So if we have a context word, river, river is dependent on the sense assignment we just chose for this instance of bank. So if you pick financial bank, the probability of river is lower because, assumingly, there aren't a lot of overlaps between this word. So, sorry, it's dependent on the sense assignment, the other sense assignments. So we have all the senses still assigned except the one we've taken out, and all of the other context words. So the probability of river in this sense we're just about to assign is high if river is common in the sense we've chosen for it. And beta governs how sensitive the model is to noise, which means in our first feature set where we had no words taken out, the and of and less useful words are very common. And so if beta is saying, let's be less sensitive to noise, it'll pay attention a little bit more to the less common features. So we want to find the best or a high probability distribution of the sense assignments for all the instances of the word bank. So we use Gibbs sampling. which just means that we repeatedly choose a new group for each instance of the word bank over and over again until the probability converges. And so that's our method, essentially. That's what it does. So I'm going to talk about evaluation and the results I have. Word sense disambiguation and discrimination is kind of tricky to evaluate because there isn't a lot of manually tagged data. And different people choose different sets of data to evaluate on, and there's not much correspondence. So some people choose to evaluate on pseudo-ambiguous words, which just means you take one word, banana, and another word, elephant, and you put them together and you get a new word, banana elephant. And everywhere in a corpus that you see either word, you replace it with banana elephant. Now, banana elephant is an ambiguous word. It could either mean banana or it could mean elephant. And so people tend to test on that a lot because it's very easy to generate. There's also the Sense Eval competition, Sense Eval 1 and Sense Eval 2, and they have training and testing label data. And there's also the line corpus, which from before we were talking about the different meanings of the word line. There are 6 meanings of the word line in this corpus, and they're all pretty distinct. And there are a few other corpora that people have done evaluations on. And so for unsupervised discrimination, it's a little difficult too because you don't have these labeled senses. So you have sense 1, sense 2, sense 3, and you have these labeled senses, financial, river, turning. And so the overall accuracy is just what's the best possible lineup of sense 1 to one of the labeled senses, sense 2 to one of the labeled senses, sense 3. And if there's more senses in the automatic assignment than in the original assignment, or vice versa, then some senses just get thrown out. There is no mapping between the original and the automatic. And so the baseline people compare to here is against majority sense, which is just the most common word sense. What is it? And how much, what percentage of the total is it? So again, there are different methods in the previous work, supervised, unsupervised being no sense labeled training data, and completely unsupervised, no labeled data of any sort. Supervised seems to do pretty well overall and beat the baseline a decent part of the time. Unsupervised does too, but the completely unsupervised has a much harder time beating the baseline in all of the previous work that I've seen. And so for the initial testing that we've been doing, we chose 14 nouns from Sense Eval. The way I picked them was to look at them and say, can I see the difference here? Is there a distinct enough difference? Because when I was looking at some of the words, there really wasn't much of a distinct difference. The word day, for instance, could mean a 24-hour period or the amount of time one is awake or working. And I would read through the corpus and not have a very good sense of which one it should be. So I chose nouns I was more sure about. And then I also chose a subset of them where I was really sure I could definitely tell the difference. And I did experiments on both of our finite and our infinite models and played around with the hyperparameters. And again, compared my accuracy score to the majority baseline. On the full set, on both versions, there isn't a significant difference between the finite and infinite models, which is good. 8 words of the 14 scored above baseline. And we found that the infinite version tended to prefer only 2 or 3 senses, whereas Sense Eval had maybe 5 or 6 on average. And I think this is good because some of the sense distinctions are pretty arbitrary. It might be easier and make more sense to people to collapse the senses into very distinct ones. I was surprised to find that my hand-chosen subset that I thought were more obvious didn't do really any differently than the original one. I ran this last week, so I'm not actually sure why yet. That's what I'm looking into now. And my continuing work is to try different features, mainly surrounding context words. are sometimes useful, sometimes not. So I'd like to look at the dependency information locally. Also, words that co-occur, so pairs of words that are often seen together in the contexts. And taking distance, right now all of the context words have sort of equal weight regardless of how far they are from the ambiguous word. And so I'd like to take distance into consideration. Closer words are more useful than further away words. I'd also like to look into topic modeling, where you choose, as well as choosing a sense, before that you choose what topic the article is on. So is this an article about financial information, or is this an article about rivers? Before you choose which topic the article is in, and then that can help you figure out which sense it is. And I'd also like to choose the hyperparameters automatically. Right now I've just been fiddling around with them a little bit, and so I'd like to do that. And that's all. Does anybody have?
I think we should ask questions right now before we listen to the second talk. So, questions? I have a question.
Mm-hmm.
Yeah.
I may have missed something, but are your texts on input already part of speech tagged before these programs are invoked?
No, I just use Eugene Charniak's parser, which part of speech tags and then parses.